When studying linear motion, we end up with these two basic equations, the velocity as the displacement in time and the acceleration as the change in velocity in time. When talking about linear motion, Newton described motion as being comprised of 5 variables: the initial velocity, final velocity, the acceleration, the displacement, and time. It's important to note that the initial and final velocities are hidden within the change in velocity here, where we define the change in velocity as the final velocity minus the initial velocity. And then it stands to question which v this is. And it's important to note that in a constant speed situation, the velocity here is both v naught and v, because the speed is averaged over that time. And so it's important for the purposes of this derivation, it's important to note that the average velocity is the displacement divided by the time, which we'll get into in just a second. What Isaac Newton did was take these two basic fundamentals of motion, combined with the idea that there's only 4 descriptors for motion, in order to rearrange these variables to become a more useful toolkit, basically math derivations. The first of which is a relatively simple rearrangement of my acceleration equation. So if I start with the acceleration as the change in velocity divided by time, as I started, I know that the change in velocity is the final velocity minus the initial, so this can be substituted in here for the delta as v minus v naught over t. Then through some simple algebra, we're going to simply rearrange by multiplying by t and adding v naught. And so we end up with a formula that the final velocity is v naught plus a times time. This equation is a straight rearrangement of the original acceleration equation, but it's also useful and valuable to think about it in terms of the final velocity being a function of the initial velocity plus the accelerated time frame. Each equation solved for a specific purpose, and we'll come to that purpose in the end. Our second derivation is going to be based on the fact that the average velocity is depicted over a constant acceleration, right? Whether or not I'm doing a constant acceleration of 0, as in moving at a constant velocity and therefore having no acceleration, or I am changing, but that change is a held number that does not deviate, then in both cases I can calculate averages in exactly the way you would calculate your grade. Averages, or average velocity, not a vector but instead just a bar over top, is the sum of the 2 known velocities divided by the number that you know. So the average velocity is the sum of the 2 velocities divided by 2. This only holds true if the acceleration is constant, right? And so that is a major assumption and stipulation for Newton's equations of motion. Nevertheless, using our v equals d over t equation, we can derive the next useful formula. So starting with v average equal to displacement divided by time, and then taking this knowledge and substituting in, I have v plus v naught divided by 2 equal to displacement divided by time. And then with just, again, with some simple algebra, we're going to rearrange this as a function for displacement. So I'm going to pull the 1/2 out as a quantity of v plus v naught and then multiply by t. And so I end up with an equation that looks like this, that describes the displacement as the average velocity times the time, which is this equation. So far the 2 equations that we've derived are simply rearrangements of the equations that we started with. Moving on from these 2, we can derive 2 other equations that will be of interest. Equation number 3 comes from the knowledge from this original equation 1. So if I start with the fact that v equals v naught plus at, then I can rearrange this and solve this for time. So by subtracting v naught and dividing by a, I end up with a time as the difference between the velocities, or the change in velocity, divided by the acceleration. Furthermore, if I then take my d equal to 1/2 v plus v naught times t, and substitute this in for that, then I'm going to get a much longer equation that can be simplified. I have 1/2 times the quantity V plus V naught times the quantity V minus V naught over A. To pull things together, I'm going to multiply by 2 and multiply by A, so I get something a little bit simpler on the right-hand side as 2AD on this side, and then the quantities multiplied V plus V naught times V minus V naught. This polynomial multiplication is a special case where I have the same terms added in one case and subtracted. This is called a difference of squares. When I do that, the middle term drops out because it would be V times V naught as a negative and V naught times V as a positive, so plus and minus cancels, and I end up with 2AD equal to the difference of squares, V squared minus V naught squared. And so this whole quantity just reduces to this. Then collecting terms and putting it in a format that's similar to equation 1, I'll add V naught squared, and then I'm going to flip the whole thing around and get my final velocity as a function of my initial velocity squared plus 2 times A times my displacement. This third equation has a similar format to the first equation, but has slightly different variables. And then the last is the fourth derivation, begins with our displacement formula that we have here as d equal to 1/2 v plus v naught times t. And then we're going to use the information from our first equation that the final velocity is the initial velocity plus the acceleration times time to substitute in there. And so utilizing my v equals v naught plus at, we're going to take all of that and put that right there. And so this turns into a much longer string of 1/2 the quantity v naught plus at, which if we wanted to, we could put that in parentheses so as to indicate that's what's changed, plus my v naught from the original equation times time. Now I'm just adding within this quantity, so I drop these parentheses, and then what I end up with is 2 v naughts. And so I have d equal to 1/2 of 2 v naughts plus at, and then that quantity times t. And so there's a couple quick hand things that we'll do, which is distribute the two outside terms. So if I distribute in, I end up with at over 2, and this drops that 2. And then distributing the t, I get v naught t and at squared. So this equation quickly becomes v naught t plus 1/2 at squared. Taking at the face of it, equations 1, 2, 3, and 4 really are the first two equations that we started with. But what you'll notice is that there is a purpose for doing each one. If you go back to our list of variables, v, v naught, a, d, and t, and you think about your process in algebra, in order to solve for a variable, it has to be contained within the formula. But it's also important that with 5 variables, there may be information that we do not know, that is not presented, that cannot be used to solve. And so an easy way for deciding which equation to use, once I've drawn my picture, listed my variables, and set up the scenario, is to select an equation based on which variable it is missing. And so keeping in mind v, v, d, a, and t, and I look at this first equation, v, v, a, and t, this equation does not have displacement. Second equation, d, v, v, and t, this equation does not have acceleration. This bottom equation, v, v, 2ad, does not have time. And this last equation does not have final velocity. And so each one is relevant to a problem based on information that may be missing, and how we transition from one to the other in order to fill in variables that may be missing is by solving a system of equations that contains both. The key component here is recognizing that all 4 of these began as these two equations of motion under a very specific constraint that the acceleration must be held constant. as a whole, these equations are referred to as Newton's equations of motion.